Welcome to The Explainer. Today, we're going on a seriously fascinating macro to micro journey inside one of the most powerful pieces of consumer technology ever created, the NVIDIA GeForce RTX 5090. You know, we're always hearing about teraflops, megahertz, and AI performance, but how does a modern graphics processing unit actually work under the hood? Well, we're going to strip away the cooling fans and the metal shrouds to look directly at the silicon architecture, zooming all the way down to the microscopic math that makes photorealistic virtual worlds possible.
Okay, let's dive straight into this. Here is our roadmap for today. We'll start with the RTX 5090 revealed, then move into VRAM and the memory hierarchy, step inside the streaming multiprocessor, check out ray tracing and the RT cores, and finally wrap it all up with matrix math.
So, Section 1. The RTX 5090 revealed. Chip versus card. When you go out and buy a graphics card, you're usually buying this massive board, right? Giant coolers taking up literally half your PC case, but the actual magic, it happens right here on this tiny piece of silicon. This is the Blackwell GB202 GPU die, so it's absolutely crucial that we separate the physical card from the chip. This die is the actual compute engine. It's the brain of the whole operation. Everything else on that massive piece of hardware really just exists to feed this chip power, keep it from melting down, and, connect it to your monitor.
To really appreciate the sheer scale of this new Blackwell architecture, we got to look at the numbers, because the leap from previous generations is just staggering. Think about it. The RTX 3090 had 82 streaming multiprocessors. The 4090 bumped that up to 128. But the RTX 5090, a massive 170 active SMs. No way, right? Plus, it's rocking 32 gigabytes of the newest GDDR7 VRAM, which delivers an unbelievable memory bandwidth of 1,792 gigabytes per second. What you should really take away from this is that we aren't just looking at some minor speed bump here. We are looking at a massive structural expansion of raw parallel compute capacity.
Moving right along to Section 2, VRAM and memory hierarchy. Let's talk about the data highways.
Now, what's really interesting is how the RTX 5090 actually achieves that blistering 1.792 terabytes per second of bandwidth. It uses brand new GDDR7 memory with something called PAM3 signaling. Now, without getting completely lost in the electrical engineering of it all, PAM3 essentially uses 3 voltage levels to transmit 1.5 bits of data per clock cycle. That's a huge step up. This higher frequency, lower voltage approach gives us literally double the data rate and double the efficiency of older GDDR6 memory. And both capacity and bandwidth are critical here. Capacity determines just how massive your AI models or high-res textures can be, while bandwidth dictates how unbelievably fast all that data can be shoved right into the processor.
But here's the thing. Memory isn't just one giant pool. It's built like a hierarchy. Imagine VRAM as a massive warehouse. It holds a whopping 32 gigabytes of data. But, it takes a relatively long time to go fetch something from the back of a huge warehouse. As we move closer to the actual processing cores, we hit the L2 cache. This is a smaller, way faster staging area, sitting at about 96 megabytes on the 5090. Then, we step down into the L1 cache and shared memory, right inside the processors themselves. And finally, we reach the registers. Think of registers like a workbench sitting right in front of a worker. It's incredibly small, but accessing it is absolutely instantaneous. So to hit peak performance, the GPU is constantly trying to move data out of that slow warehouse up to the lightning-fast workbench and reuse it as much as possible before sending it back.
All right, on to Section 3, inside the SIM. Welcome to the GPU factories. So, if we look closer, the GB202 chip is divided up into graphics processing clusters, which contain texture processing clusters, which finally house what we call the streaming multiprocessors, or SMs for short. The full chip is packed to the brim with 192 of these SMs, with 170 of them active on the RTX 590. And these SMs, they are the absolute fundamental workhorses of the entire GPU. Literally everything from rendering realistic lighting to calculating complex AI physics, it all happens right inside these blocks.
Now, to really get why a GPU SM is so special, we kind of have to contrast it with your computer's main processor, the CPU. A CPU is sort of like a few highly intelligent executives and has a small number of very large, highly complex cores designed to execute tasks sequentially, one right after the other, incredibly fast. A GPU, on the other hand, is like an army of thousands of specialized workers. It runs on a model called SIMT, that stands for Single Instruction Multiple Threads. So instead of doing one really complex task quickly, it takes a single, simple instruction and applies it across thousands of different pieces of data all at the exact same time.
And here is exactly how that SIMD model breaks down. The smallest unit of work is a thread. Threads are then grouped into blocks that can share memory. But the real magic word you need to know here is the warp. The SM scheduler organizes work into warps, which are basically fixed-size groups of exactly 32 threads. And these 32 threads execute the exact same instruction in perfect lockstep at the exact same time, just working on different data pixels. If you can keep all 32 of those threads doing the exact same thing without diverging, well, that's when the GPU operates at peak massively parallel efficiency.
Which brings us to Section 4, Ray Tracing and the 4th generation RT cores.
Before we even look at the hardware, let's take a second to establish the fundamental shift that ray tracing actually brings to the table. In older games, shadows and reflections were basically faked, right? They used clever visual tricks and painted on textures. But ray tracing, it stops faking it. It literally simulates physical reality by shooting millions of invisible light rays from your virtual camera straight out into the scene. The computer then calculates exactly how those rays bounce off objects, absorb color, and cast shadows, just like light does in the real world. It creates absolutely stunning realism, but the math required to test if a tiny ray hit a virtual triangle is just punishingly difficult for a computer.
And that exact difficulty is why the RTX 5090 has dedicated hardware solely for this task. Tucked inside every single one of those 170 SMs is a 4th generation RT core. We aren't talking about software here. This is a physical silicon engine built exclusively to calculate light ray intersections. In fact, this new Blackwell architecture provides double the ray triangle intersection throughput compared to the previous ADA generation. It takes all that heavy lifting completely off the main processor's plate, freeing up the rest of the SM to just focus on painting the colors and graphics.
This new RT Core also brings some seriously incredible new tools to the workbench. For instance, it includes a triangle cluster intersection engine designed to handle what they call mega geometry. This lets game engines ray trace highly detailed, literally movie-quality assets in real time without having to fall back on blocky, low-resolution proxies. But here is a truly surprising fact for you. Calculating how light hits thin, curved strands of hair or fur is traditionally an absolute nightmare for computers, like notoriously difficult. So Blackwell introduces linear swept spheres. Basically, the RT Core now has a dedicated hardware-accelerated physical path designed specifically and exclusively just for rendering realistic hair and fur. How wild is that?
Okay, last but not least, Section 5, Matrix Math, Parallelism, and AI.
You know, we hear the term AI thrown around constantly these days, but at a hardware level, artificial intelligence is almost entirely just matrix multiplication. It's just taking massive grids of numbers and multiplying them together. And why this matters to you is that this matrix math is the actual heartbeat behind incredible tools like DLSS, deep learning supersampling, and neural reconstruction. Because of this math, the GPU can render a low-resolution image, and the AI will just magically generate the missing pixels, handing you a crisp 4K image at double the frame rate.
Now, you obviously can't multiply a billion parameter matrix all at once, so let's see how this builds. First, the massive matrices are broken down into smaller chunks, called tiles. The threads load these tiles from that giant VRAM warehouse we talked about earlier right into the SM's shared memory. Then, the data moves onto the workbench, the registers. Finally, the highly specialized 5th generation Tensor Cores take over, performing thousands of fused multiply-add operations per cycle. Basically, they multiply the numbers, add the result to an accumulator, and write it straight back. It's this continuous, relentlessly efficient loop of data crunching happening across hundreds of warps all at the exact same time.
And honestly, that is how a modern GPU really works. It's like an intricately designed city made up of memory warehouses, super-fast data highways, and parallel worker threads, all perfectly orchestrated to calculate light and AI matrices at speeds that are, frankly, kind of hard to comprehend. The sheer scale of the RTX 5090, with its massive bandwidth, dedicated ray tracing engines, and unbelievably fast tensor cores, is just a massive leap forward. So I want to leave you with this thought. With billions of transistors now capable of running complex generative AI and physical light simulations simultaneously, in real time, what completely new, never-before-seen virtual experiences is this hardware going to unlock for us next? The age of neural rendering has truly arrived. Thanks for hanging out with me for this explainer, and keep learning.